Again, you remember that we said how the understanding of the flow behavior, how the velocity components they are acting. This we have found out with the help of equation of continuity and equation of motions. We also have done on the application of these equations, how we can solve with the help of these equations some of the problems we have done, right? And where the Navier-Stokes equations, understanding of the individual components of the equation, that we have shown, right? Obviously, as and when your problems will be complicated, your solutions also will be complicated, but depending on the cases, we assume something which are valid, not only valid, which can be really assumed, and in all cases where this is more feasible, those things we have dealt with, right? Now let us go into some other which are really further required for your not only understanding but also applications. For example, if you are in industries, you are dealing with flow through pipes, right? You have seen, if you are in the hostels, that your pipe is coming, the fluid is coming through, or water is coming through some pipes, and those pipes are maybe somewhere some horizontal, somewhere vertical, depending on the cases from where it is coming, etc. And one more very good example is that when you look at, this is the real picture of the hostel scene, wherever it be, that some or other day, if you are fortunate enough or rather unfortunate enough to come across such situations, that you started taking bath and suddenly there was no flow in the toilet or in the washroom. It may happen, it might have happened to many of you who are students in our students' life, in the hostel life. This is a common situation everywhere, right? And then when after shouting and after doing and this and that, some people went to the supply, and again supply came up, and when this supply is coming, then initially at the time first when it came, it was not coming fully, it was coming a little sprinkle like thing, a spot, a little flow and then stopped, a little flow and stop, with the sound like push 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 push, like that, this kind of sound they used to come. And then we could come to know, yes, now the water is again coming, and after some time the fully developed flow is to come, and this situation is also applicable in many cases, right? Now what we will look into is that pipe flow, or flow of fluid through the pipes, or we call flow through pipes, or pipe flow, or flow through circular tubes, right, or conduits, anything it can be. So that we have a circular conduit through which fluid is flowing, like that. If it is a pipe, in this the liquid is flowing from one end to the other end, right? In this, certain assumptions we make, those assumptions we have to follow, and these assumptions are like, we will do the shell momentum balance inside a pipe, there is no ambiguity. So we will make a we shall make a shell momentum balance, that is, we will take a shell in the pipe and we will do the momentum balance in that shell, and then integrate over the entire region of the pipe, right? Some conditions which we are imposing, that the fluid is incompressible, right? The fluid is incompressible, it can be Newtonian. So, if it is Newtonian, then that power law which will come afterwards, power law equations, they are becoming very simple. So, it is Newtonian equation or Newtonian fluid, rather incompressible fluid, that is again incompressible fluid means the fluid is having constant density, right. Flow is one dimensional, steady state as well laminar. So, these conditions we are imposing in the beginning, that what is the situation? Flow is laminar, flow is steady, fluid is incompressible, and the fluid is Newtonian fluid. So, these things along with the flow is fully developed, right, as we said, the flow is fully developed. If you think that you have a reservoir here, right, like this, and with that some pipe, there is a say valve here, right. In this valve you open, then there will be some point when it will be like this, right, till the flow becomes a continuous flow, as we gave the example of this hostel, right. So, that flow is fully developed. This flow is fully developed and there is no end effect. This is what we are saying. End effect means in the pipe, that whenever it is coming in, there will not be such this kind of maldistribution of the flow, right. This in either side of the pipe is not there. So, it is no end effect is also there. This flow is fully developed, there is no end effect, and velocity profile does not vary along the flow of the fluid, right. This also we are imposing, velocity profile does not vary along the flow of the fluid, right. So, these conditions we impose, right, and then by doing a shell momentum balance we can tell. Now, shell momentum balance means here we are taking that shell, this is the section of the pipe. We assume that in this pipe is in the R and X direction, right. If we assume it to be horizontal pipe, so Z direction is not there. So, it is horizontal. So, in that case Z direction is not there. So, R is this in the pipe radius and X is the flow of the in the direction of the flow, right. This we are taking, and in that we have taken a shell like this. This shell having a thickness of delta x, right, having a length rather of delta x and say thickness of delta r, right. This shell we have considered, this shell of delta r we have considered, right, and we will do the shell, this shell in this momentum balance we will do, and this is called shell momentum balance or control volume for shell momentum balance on a fluid flowing in a circular tube or conduit that we are dealing with. So, this we will do today, that is the flow through the pipe, right, and we assumed to be horizontal pipe, we assume the flow to be fully developed, we assumed it is a steady state, we assumed that the fluid is incompressible and the fluid is also Newtonian, and also we assume that there is no end effect in the flow and there is no velocity component or there is no velocity profile changing along the flow of the velocity profile is not changing along the flow of the fluid. These assumptions we have made in the beginning, and we are doing axial momentum as we have shown in the diagram in the slide, that we are taking a small elemental volume in that pipe section, and this will do the momentum balance on the shell and then integrate over the entire pipe, right. So, to do that, now let us do that. The governing equation is the rate of momentum in minus rate of momentum out plus sum of the forces acting on the volume element is equals to rate of momentum accumulation, right. Now, momentum can be transferred, as we said earlier also, it can be transferred by two ways. One by the bulk momentum, that is the bulk flow of the fluid. When the fluid is fully flowing, the bulk flow of the fluid is one way of transferring the momentum, and the other one is by the shear force. That is, though it is laminar, but we said that the though laminar, but the fluid we can assume the layers to be so close, so small that the molecules they vibrate, and due to the vibration of the molecules there will be the transfer of energy, and that is we said earlier by the molecular momentum transfer. This we said earlier. So, in this case, since it is a steady state, then we can say momentum in by the flow or convection is equals to momentum out by convection, right. So, momentum in and momentum out both are same because it is a steady state. So, by bulk flow there is no momentum getting transferred, right. It is a steady flow. Then the momentum in by molecular transport momentum in by molecular transport is tau r x 2 into area 2 pi r at the phase delta x r, right. 2 pi r delta x r at the phase r, 2 pi r delta x is the area, and at the phase r. Similarly, this is momentum in by molecular transport. So, momentum out by molecular transport at the phase r plus delta r is tau r x, right, 2 pi r delta x at the phase r plus delta r, right. And then out of some of the forces acting on the shell, we can say that pressure force in is equals to P at the face x, and that is equals to P into area 2 pi r delta r at the face x, and pressure force out, that is equals to P at the face x plus delta x, that is equals to P into 2 pi r delta r at the face x plus delta x, right. So, if we now apply that the control control equation which we had started with, right. If we apply that, now we can say that tau r x 2 pi r delta x at r minus tau r x 2 pi r delta x at r plus delta r plus P 2 pi r delta r at x minus P 2 pi r delta r at x plus delta x, right. This is equals to 0, or we can now divide with delta x and delta r in all the cases. Then this becomes we can divide this 2 pi r delta r into delta x, that is the volume, right. 2 pi r delta r to delta x. So, if we simply divide with this, then we can write r tau r x at r plus delta r minus r tau r x at r over delta r. This is equals to r times P at x minus P at x plus delta x, right, over delta x, right. So, from the definition of the derivative, we can write from these two that this can be written as del r of r tau r x, right. This is equals to, since this is P x minus P at x plus delta x, from the definition of derivative, it is P at x plus x minus P at x over delta x is the derivative. So, it becomes one negative. So, del x of P this into r is this side, right. So, we can write that this is del r into r tau r x is equals to minus r into del p del x, right. Now, del p del x is nothing but minus del p del x into r is equals to, this is del p, delta p means you have this pipe, this is P inlet, this is P outlet, right. So, P inlet is higher than P outlet, otherwise there will be no flow. So, P inlet is higher than P outlet, but from this definition it is P outlet minus P inlet by delta x, that is negative, right. So, from there we can write this is delta P over, if this length is L, right, if the total length of the pipe is L, delta P by L into R, right. So, why this negative has gone out, you hopefully have understood that delta P is from inlet high to outlet low, right. By definition of this derivative, this is P outlet minus P inlet by del x, that becomes the derivative. So, this negative has been taken care of by delta P where this is nothing but is equals to P in minus P out over L into R, right. So, if this be true, then we can write del L R of R tau R x is equals to delta P by L into R, right. So, on integration we can write that R tau R x is equals to delta P, which is constant, L which is constant, this R is R square by 2 plus C R by plus C. So, we can write tau R x is equals to delta P over L into R by 2 plus C by R, right. So, this we can write. So, therefore, we can say that tau R x is delta P over L into R by 2 plus C by R. Now, if we put the boundary conditions are what? At R is equals to 0, since tau R x is not equals to infinity, at R is equals to 0, since tau R x is not infinity, we can write C is equals to 0. At R is equals to 0, since tau R x is not infinity, then if at R is equals to C has to have some value, then tau R x has to have infinite value. Since it is not infinite, it is having a finite value. So, C is equals to 0, right. Then we can write tau R x is equals to delta P by L into R by 2 or R delta P by 2 L as the tau R x, right. So, this is in general we will use this subsequently in many cases you will see that we will tell that this when we are doing the either shell momentum balance or similar, we will tell that we will starting from here. If there is no bulk flow or effect of bulk flow is negligible or not negligible, it is not there, it is steady by any chance, and then we will start in many cases when the fluid will be Newtonian, you will non-Newtonian, you will see that we will tell that we start from here, that tau R x is equals to R delta P by 2L or delta P into R by 2L. This we will start with, right. You remember this, that this is the starting point in many cases we will say. Okay. Now, since by definition tau R x is nothing but is equals to minus mu dVx dr. So, on substitution we can write mu dVx dr is equals to minus delta P over L into R by 2, right, or dVx dr is equals to minus delta P over 2 mu L, right, into R, right. So, on integration we can write Vx is equals to minus delta P 2 by 2 mu L, right, into R squared by 2 plus the integration constant C1, right. So, if we write like this, then we can also write that the boundary condition, is what? at r is equals to capital R, at r is equals to capital R, V x is equals to 0. That was this, right. So, this is the axis and this was R, right. This was delta L or x axis, this is delta L, rather this way, right. So, this is delta x, or in the x axis this is r axis, r and x. In that case, at V x is r is equals to r, this r is equals to r is capital R, right. So, at that is at the wall, at the wall r is equals to capital R, V x is 0, that there is no velocity on the wall, right. The layer which is clinging to the wall, there is no velocity, that we know. So, if this is true, we can write in terms of maths that at r is equals to capital R, V x is equals to 0. Therefore, we can write this equation at C 1 is equals to V x is 0. So, C 1 is equals to delta p by 2 mu L, right, into this 2. So, that r is equals to r. So, r squared by 2, right. So, that is equals to delta p r square by 4 mu L is C 1. So, therefore, V x we can write that this is nothing but delta p r square by 4 mu L, or this is 4 mu L, right. If we take that to be common, then it becomes r square, and first this r square will come, this is plus. So, capital R square minus small r square, right. So, if we substitute here value of C 1, then it becomes delta p r square by 4 mu L r square minus r square, right. So, this we can rewrite as V x is equals to delta p means p in minus p out, right, into r square. If we take this r square to be there by then this r square does not come, right. This if we take r square inside, then this does not come, right. The by 4 mu L, now we can write this 1 minus r by r whole square, right. So, if this is true, then V x is p in minus p out r square by 4 mu L to 1 minus r by r square, right. So, this is the velocity at any point. This is the velocity at any point x. Now, if we have the average velocity V average, that can be written as 1 by area integration of V x to d area, right. V x d this area, right. Now, this velocity we can substitute with the V x value. This is 1 by a into integration of this area is V x r d theta dr. This is the elemental volume, right, r d theta into dr, that is area, and this varies between 0 to r, and this theta is varying between 0 to 2 pi. So, that we can write, and this area we can write 1 by pi r square to be the area, right, and we can say this is 2 pi r dr d dr rather V x, right. So, on substitution of the value of V x, we can write 1 by pi r square, right, integral of r into delta p by 4 mu l, right, into r square minus r square, right, into dr. This on simplification we can write, this is again between 0 to capital R. So, 1 by pi r square, 1 by pi capital R square, and this on simplification can be written as 2 pi r. Okay, this pi r, 2 pi r, that comes out. So, pi r square here. So, that means this pi r that goes out, right, from here. So, we can then write as this is equals to P 0 minus P L by 8 mu L into R square, that is equals to P 0 minus P L by 32 mu L d square, right. So, V average then is equals to P in minus P out, right, over 32 mu L into d square. If it is R, then 8, otherwise it is D, right. If it is 8, then R, then if it is 32, then D. So, P in minus P out by 32 mu L is V in, V average, that is P in minus P out into D square by this. This is called Hagen-Poiseuille equation, right. P-O-I-A-C-U-I-L-L-E, Hagen-Poiseuille equation. This is a famous equation which is equation for pipe flow. If you are asked, then that under steady state, if the flow is laminar for a Newtonian fluid, how can you find out the pressure drop? So, you can say you can use the Hagen-Poiseuille equation and find out the delta P over that, and with this equation that the V average is delta P into d square by 32 mu L, that is the Hagen-Poiseuille equation. Obviously, one more thing here we can average, we can find out V max, right. V max is equals to delta P, that is P 0 minus P L R square by 4 mu L. This is true at R is equals to 0. So, from this equation which we had gone through, that from this equation, that this on integration in terms of R, if we put R is equals to 0 here, then we can say the delta P R square by 4 mu L is the V max. Therefore, that can be said that V average is nothing but V max by 2, right. Average velocity for a pipe flow is the maximum velocity by 2 or V max by 2 when the fluid is incompressible, fluid is under laminar steady, there is no end effect, there is no velocity profile along the flow of the fluid in the pipe, and in that case we can say that average velocity is half of the maximum velocity, right. So, here we stop today, and thank you. I think that we can show. Okay. So, thank you.